Let's continue with our classifying of matter a little bit more. Now, as you know, there are three states of matter that we encounter on Earth. We have solids, liquids, and gases. So anything that's an atom or an element or a compound that combine into mixtures will exist in one of these three phases. There actually is a fourth phase of matter called a plasma that is common as well, but we won't encounter it too much in chemistry class because plasmas are electrically charged gases. They're only found in very high energy states. But the main thing that distinguishes a solid from a liquid from a gas is just temperature. At low temperature, atoms have low energy, so they generally are close together, and they exist as a solid. And at high temperature, you cause the atoms to move with higher energy, and they exist as gases, and in between as a liquid. So this is all pretty intuitive, I think, but a visual picture of what's going on, or how we characterize or distinguish between the three is as if you put a solid in some sort of empty container, it's going to maintain its shape and it's going to maintain its volume because it's locked, all the atoms are locked into position. You put a liquid in a big empty box and it's just going to assume the shape of its container. It's going to have a fixed volume, kind of like a solid, but it will assume whatever shape of container you put it in. And that's because the molecules are moving fast enough and they're kind of sliding over each other. We experience that as a liquid. If you heat the sample even more, you can cause the molecules and atoms of this liquid to escape into the gas phase. At room temperature, actually, the air molecules that you're breathing in are moving at about 1,000 miles an hour. We'll spend an entire chapter of this course just dealing with the behavior of gases. But that's really all that distinguishes the three states of matter is temperature. But there are other reasons we'll talk about that talk about why something is a gas at room temperature versus why it's not a liquid versus why it's not a solid. Why is something a solid and why is it a gas? There are attractive forces that exist in nature that hold things together that we use to explain this. But just because something is a gas on Earth doesn't mean it's a gas everywhere in the universe. For instance, the gases that you might find that are common on Earth at room temperature are things like we've talked about carbon monoxide. That's a gas you don't want to come in contact with. CO2, hydrogen, nitrogen, oxygen, these are the components of air. Hydrogen, you're not going to find too much floating around the air because it's very reactive. But we do use that in chemistry labs to do a lot of things. Versus why are these liquids at room temperature? So remember I had those models out earlier, like this represents hydrogen, that's a gas at room temperature. This is nitrogen, that's a gas at room temperature. This is oxygen, that's a gas at room temperature. This is carbon dioxide. These are all gases at room temperature. But water is a liquid at room temperature. Why is that? Well, if you look carefully, what are you seeing? Well, this is a straight line. This is a straight line. Just ignore that those are curved. That's just representing electrons that are holding them together. This is a straight line. This is a straight line, but this is bent. This is a V shape. If you were able to see water molecules that you're drinking, they would actually be countless numbers of these little V-shaped molecules. This is why water is a liquid at room temperature, because of its shape. That's pretty crazy. That's cool. And we'll talk about that in this class. Why is water bent? And then what does that cause? What does that mean? It means that water, because it's bent, is a liquid at room temperature. And we're here alive on Earth because of water. Water is the basis for all of life. So this is what chemistry helps us understand. The basic structure of molecules has very important consequences. But just because something is a gas here doesn't mean it's a gas somewhere else. Things that are solids at room temperature generally are larger molecules. So sugar is made of the same elements as CO2 and hydrogen, but it's just a larger molecule. It's made of about, I don't know, 20 atoms or so. Salt, which is only made of 2 atoms, like carbon monoxide is, that's a solid at room temperature. Why is that? Why isn't that a gas? Because that's made of 2 atoms. This is made of 2 atoms. Why aren't they just gases? Or why is that not a solid? These are all reasons we're going to discuss. Sodium hydroxide is a solid at room temperature. But if you went to a different planet, a molecule's physical state depends on where you find it. For instance, like I said, on Earth, these are all gases because the temperature is about 20 degrees Celsius. It's about, I don't know, 70 degrees Celsius average temperature on Earth. 70 degrees Fahrenheit, I'm sorry. But if you went to a planet like Jupiter or Saturn, which someday we may be able to travel to, you'd find these gases existing as liquids, and sometimes even as a solid if it really gets cold. The temperature on, that was a mistake, the temperature on the surface of some of these planets is negative 290 degrees Fahrenheit. So when you get to such a low temperature, these molecules slow down so much, because that's all that temperature really is a reflection of how fast something is moving. When you get to such a cold temperature, things that are gases on Earth will become liquid. So keep that in mind when you are talking about the physical state of something. It does depend on where it is. That fourth state of matter I was talking about, the plasmas, I think you can see that here, is not something we're going to talk about too much, but it is extremely important. Plasmas are ionized gases, and you can form a plasma if you take a gas and you either give it what's called electromotive force, zap it with microwaves or hit it with a laser beam. You can convert gases into plasma, and that's what's going on inside of a plasma TV or in a neon sign. A neon sign is just an electrically charged gas of neon and some other elements. Lightning is a plasma. Stars are mostly plasma. Fire is a plasma, believe it or not, and the northern lights. So really, when you think about it, most of what's out there in the universe exists as plasma. On Earth, most things exist as solids, liquids, and gases. So when you think of how we fit in on Earth into the grand scheme of everything, we take up a very tiny portion of all the matter that exists. You couldn't even measure how small our Earth is relative to everything else, and we only use a very small percentage of the type of matter that exists. Most matter exists as a plasma state. But since this is a chemistry class, we have to deal with the things we can handle. It's hard to deal with plasmas safely, but in chemistry class we can manipulate matter that exists as a solid, liquid, and gas very, very well. We've learned to do that very well. The alchemists back in 400 years ago, they were more like magicians. They were trying to do chemistry before they really understood what it was, and they were trying to convert things like mercury, elements like mercury, into gold, and they weren't successful. So we can further classify matter. We call a generic thing out there matter or a substance. So something that's a substance is either an element or a compound or a molecule. What distinguishes an element from a compound? So remember, I said that these are the elements. These are atoms that are made of just one. Elements are things that are made of one type of atom, whereas compounds or molecules are made of more than one type of atom. So if you want to classify or distinguish between an element and a compound, elements are things that cannot be broken down by chemical means. You can break them down by nuclear means, but since a chemical reaction cannot break down an element, it just converts the element, or it shuffles the elements around. Compounds or molecules can be broken down by chemical means. Or they can be rearranged, broken down, or changed by chemical means. When I say chemical means, I mean a reaction. A chemical reaction is a brief summary, it's a symbolic summary of a chemical reaction. So a chemical change. So for instance, if you burn methane, a chemical reaction would be CH4 plus oxygen gives you CO2 plus water. That's a chemical reaction. That's called combustion. And then there's an even better way of further classifying matter. It kind of summarizes everything I've been saying. Let me get my chart here. I think I should just show you this. Well, no, I'll draw it out for you in case you're taking notes. So let's just draw a little chart to show you how everything kind of fits together. So let's just say everything is matter. That's everything. So what is everything made of? Well, we say it's either a mixture. Most things you come across are a mixture, or it's a pure substance. There's a chart like this in chapter 1, I'm sure. Now, what are some examples of mixtures and pure substances? Well, there's many. Seawater is a mixture. Rocks are a mixture. What are pure substances? Things like water, CO2, sugar. When I say sugar, I mean table sugar, table salt, sodium chloride. Those are pure substances. Now, how do you go? Can you convert a submixture into a pure substance? Yes, you can. You can go back and forth between these, a mixture and pure substance, by physical changes. What are physical changes? Things like filtering or boiling or melting. You can separate mixtures into their pure substances, but you cannot take a pure substance and break it down into its constituent atoms by physical means. You need chemical means. And if you take a mixture, there's two types of mixtures. Either you have what's called a homogeneous mixture, or I think I'm running out of room here. I think that's on the page. Or a heterogeneous mixture. And what distinguishes those? We'll get to that in a few minutes here. What are pure substances? Well, if you can break it down, like I had on the previous page, if you can break it down, you have a compound. If you can't break it down, you have an element. So you either have elements or you have compounds. And what distinguishes these, or what are some examples of these? We've already seen many examples of elements and compounds. H2, iron, anything in the periodic table, silver, gold, those are elements. Compounds again, anything with two or more different atoms. I won't call H2 a compound, because remember, as I said earlier, H2 is technically an element that exists as a diatomic molecule. Okay, so I know this is a little confusing, but these are just words I'm saying to you. This is a language you're learning, so you need to understand the grammar. So what are examples of homogeneous or heterogeneous mixtures? I have some things here I brought with me. For instance, if you looked at this mixture here, this is called a buffer solution. This is a homogeneous mixture because it has uniform composition. So homogeneous mixtures have uniform composition. They look the same no matter where you look. No matter what sample whatever piece of this solution I look at, it all is this light reddish color. This hand sanitizer that I was given by the university, it looks like water, but hand sanitizer is a mixture, a homogeneous mixture. And if you look at the ingredients, you can see if it's made of more than one chemical, it's definitely a mixture. So we know it's not a pure substance. So that's a mixture, a homogeneous mixture. Heterogeneous mixtures have non-uniform composition. Now that would be something like this rock here. This rock is an example of a heterogeneous mixture. Now we call it a rock, but a scientist, a nerdy scientist like me would call it a heterogeneous mixture. It's made of many different pure substances, many different ionic compounds. You mix together, you get something like this. This has been made in the Earth's crust under tremendous pressure, so it's made of different minerals that a geologist would understand. But notice how this has different characteristics depending on where you look. This, I just got these red, we all use these, we put these on pizza, these red pepper flakes. That's a heterogeneous mixture because it doesn't have a uniform composition. There's not the same number of particles and there's varied types of and sizes of particles in there. A sample of black pepper, that is a heterogeneous mixture. It's not uniform. The appearance over here is different from the appearance over here, just like in this rock. That's how you distinguish between a heterogeneous mixture and a homogeneous mixture. Another name for a homogeneous mixture, which we'll spend an entire chapter on, I believe, are called solutions. Let's think of some examples of each of these again. So solutions would be things like, let me just put examples of solutions. Would be things like I said, seawater. You hold up seawater, or you cup seawater in your hand, it's going to look like water, so it's homogeneous. Coffee is a homogeneous mixture. Pure air that doesn't have dust in it is a homogeneous mixture. Brass, which is an alloy of copper and zinc, that's a believe it or not, that's classified as a solution. Solutions don't always have to be liquid, they can be solids mixed together. Gasoline is a homogeneous mixture. It's kind of has a bluish tinge to it, but that's a mixture of many different types of carbon-containing compounds. What are some examples of heterogeneous mixtures? It's hard to spell with these pens. Examples of heterogeneous mixtures, orange juice. You can't see through orange juice, number one. Rocks. A dusty air is an example of a heterogeneous mixture. Soda. Why is soda a homogeneous or heterogeneous mixture? You might say, well, soda kind of looks like that. Isn't that homogeneous? No, only if the soda is flat would it be homogeneous. If the kind of like if there were a lot of air bubbles, technically speaking, that's heterogeneous, but let's just assume the air bubbles weren't there. Soda has a mixture of CO2 gas and water and some other things. But when you have different phases present, gases and liquids, that means it's heterogeneous. You don't have the same phase. This is all one phase that you can see. All right, I like doing demonstrations to give you a visual of what we're talking about. So I can simply demonstrate the difference between homogeneous versus heterogeneous mixtures with some everyday objects we all have around our houses. So I've just filled the glass with distilled water. Distilled water is a pure substance, H2O, right? All right, that is not a mixture yet, but I can easily make a mixture by adding in table salt. So let me just dump a bunch of salt in. Now we know from everyday experience that table salt dissolves very well in water because that's what the oceans are. They are water with quite a bit of sodium chloride and some other trace minerals dissolved in them, but the bulk of the salt that's in the ocean is sodium chloride. So now what I've done is I've mixed two pure substances, H2O and NaCl, and I've made seawater, salty water, which is a solution. How do I know it's a solution? Because eventually that salt's going to dissolve. It still looks like water. So I can't tell salt water apart from water. So the appearance is uniform. I have a homogeneous mixture. I can also make a homogeneous mixture just by adding a drop of food coloring in. 1 drop of blue food coloring will turn this into blue salty water, but I can still see through it, so it's clear and it's still considered a homogeneous mixture or a solution. So this is a key thing I want you to describe correctly. This is not, this is clear and blue, but water is clear and colorless. A lot of people say water's clear. Yes, it is, but it's also colorless. It doesn't have a color. Something can have a color and still be clear. You can see through it. That's a solution. How do I make this into a heterogeneous solution? Well, I could bubble CO2 into it and make it into soda, so to speak. Or what if I took this substance here? This is just vegetable oil that I will pipette into the mixture. Now, what do you know about oil and water? Oil and water don't mix. They don't like each other. They don't like each other because oil is what's called nonpolar and water is polar. So it's like apples and oranges, right? You mix those together, you have a non-uniform mixture. They don't like each other. You can see the oil floating on top of the water. If I stir it up, no matter how much I stir, I will get what's called an emulsion, but I'll get a heterogeneous mixture. You see the oil just kind of forms this oily layer on top. The oil floats to the top. So now I've made a heterogeneous mixture. I know it's a heterogeneous mixture because I have different non-uniform appearances and I have different phases present. I have a oily layer laying on top of a lower aqueous blue layer. So this is a heterogeneous mixture. I hope that explains things or gives you a little visual demonstration of what we're talking about here.